In this video, we are starting section 6.2 on the pigeonhole principle. So our goals are to apply this technique called the pigeonhole principle and to recognize which types of counting problems involve the pigeonhole principle and which ones don't. So in this video, we are going to introduce the method and do some quick examples. So I want to motivate what the principle is with an example which says there are 51 students in a class, each from one of the 50 US states. So the first observation that I want to make is, because we have more students than there are states, there have to be at least 2 students from the same state. Because, I can visualize these 50 states with boxes. So I have box 1 for state number 1, a box for state number 2, state number 3, and if I keep going, there are 50 of these boxes. And then no matter how I try to spread out these students among the boxes, like if I say, there's one student from this first state and another student from the second state and another from the third state, I could keep trying to spread them out as much as I can. And even if I put one student in each of these 50 states, well, that's not enough to cover all 51. There's going to be one student who is left over who then has to be, part of one of these states. Maybe they're part of state 3 or they're part of state 50. They got to be part of one of them. So because of that, there have to be at least 2 students from the same state. So how do we prove this? How do I prove that there are at least 2 students from the same state? We can do a proof by contradiction. So we're going to proceed by contradiction. Okay, and so we're going to assume for the sake of contradiction, if my goal is to show that there is some state that has at least 2 students from it, I'm going to be assuming the opposite of that. I'm going to assume that for each state, for every state, there is at most one student from that state. Okay, because at least 2 means 2 or more, 2 or 3 or 4 or more. So negating that would be 1 or fewer, which is at most 1. Okay, so I'm assuming that there's at most 1 student from each state. So this implies that there are, because there's 50 total states, I would multiply 50 by 1, and that gives me 50. I need to say something before this. There would be at most 50 times 1, which is 50 total students. But that would be a contradiction because the problem says that there's supposed to be 51, which is a contradiction. Okay, because there's supposed to be 51 total students. That is a contradiction. Okay, so therefore, I'll write my symbol for therefore. Therefore, there is some state with at least 2 students from it. With at least 2 students from that state. Okay, so we proceeded by contradiction. We assume that each state had at most 1 student from it, but that would just give us at most 50 total students. And that's just not enough based on what the problem says, because the problem says there's supposed to be 51. Okay, so this leads us to the general principle. So we are ready to state it. So first, the basic version of the pigeonhole principle says that if there are P pigeons and H holes that you're trying to place the pigeons into, and the number of pigeons is greater than the number of holes, then there has to be a hole with at least 2 pigeons. That's what we saw in this example. If I want to prove this in general, it involves contradiction. It's very similar to what we did to prove it for this specific example, just we would use our general variables here. So I'm not going to prove it again because it's virtually identical to what we did. And then there's a generalized pigeonhole principle, which says that if I have P pigeons and H holes that you're trying to place them into, then there's going to be a hole with at least P over H if I do take the ceiling of that many pigeons. For example, if I had 17 pigeons and 5 holes to place them into, there would have to be a hole with 17 divided by 5, and then I'm going to ceiling that. Because 17 divided by 5 is 3.4, and I have to ceiling that because, for example, if I had 15 pigeons and 5 holes, well, I could place 3 into each hole, and that would be totally fine. But with 17, I'm going to have some extras. And that's what this decimal is indicating to me, that I have some extras. So the ceiling of 3.4 is 4. Okay, there's got to be some hole with at least 4 pigeons in it. With 4 pigeons. With 4 pigeons. Okay, so that is our generalized pigeonhole principle. All right, so let's do some examples. All right, so this example says that a standard deck of 52 cards contains 13 cards of 4 suits, which are hearts, diamonds, clubs, and spades. So that means there are 13 hearts, and there are 13 diamonds, and 13 clubs, and 13 spades in a standard deck of cards. So then the question says, how many cards must be selected to guarantee that at least 3 cards of the same suit are selected? So I first want to give you an opportunity to try this. So pause the video for a minute to try this. Pause it in 4, 3, 2, 1. Pause it and try it. Okay, so hopefully you tried it. Let's talk about it now. So first, just kind of thinking about this informally, if I started picking some cards, like maybe the first one's a heart, which I'll call H, maybe the next one's a diamond, and then I have a club, and then I have a spade. So if I had picked 4 cards, it's possible to just have 1 of each. So how long could I go without having 3 cards of the same suit? Well, maybe going from there, maybe the next one I pick is a diamond, and then I have a spade, and then I have a heart, and then I have a club. So if I had picked 8 total cards, I could spread it out in such a way that I just have 2 of each suit. But now, no matter what I pick for the next one, regardless of whether I pick a diamond or whether I pick a club or a spade, well, now I'm going to have 3 of the same suit. So just from kind of conceptually playing around with it, it seems like the answer should be 9. So how do I show this more precisely? So we can use the pigeonhole principle. So to do that, let's identify the pigeons and the holes. So the pigeons for this problem are the cards. Those are what we're selecting. And we're trying to place them into suits. We're trying to categorize them by their suits. So the suits are going to represent the holes here. So I know how many holes there are. There's 4, because there's 4 suits. But the number of cards is an unknown. So I'll put a question mark there. So if I use the generalized pigeonhole principle, and I know I want to use the generalized one because the basic pigeonhole principle just says if you have more pigeons than holes, there's got to be some hole with at least 2 pigeons. But anytime I'm trying to show something slightly different than just there's at least 2 of something, like here I'm trying to show that there's at least 3 of something, we use the generalized version. So I'm going to say by the generalized pigeonhole principle, GPH, there is a hole, which for my problem is a suit. There is a suit with at least, and I got to take the ceiling. I got to take the ceiling of the number of pigeons on top, which is the number of cards, divided by the number of holes on bottom, which is the number of suits, which is 4. And in the problem, I really want this to be equal to 3. Okay, so what's the smallest value this numerator could be so that when I do this ceiling, it ends up equaling 3? Well, it's got to be 9. the number of cards has got to be at least 9 to guarantee this. At least 9. So that's the answer to my question. How many cards must be selected to guarantee that there's at least 3 of them of the same suit? The answer is, gotta select at least 9. Okay, so let's end with one related example, which says, how many cards must be selected to guarantee at least 3 hearts are selected? So now it's not just saying 3 cards of the same suit, we're specifically saying that they have to be hearts. So I want to have you try this first. So pause the video for a minute in 4, 3, 2, 1, pause it and try it. All right, so hopefully you tried it. Let's talk about it now. So one important observation I want to make about this is, in part B, it's specifying which suit. It's saying hearts. So that means it's specifying which hole we want these pigeons to be in. But the pigeonhole principle doesn't tell us it doesn't tell us anything about the specific hole. It just says that there's got to be some hole with at least some number of pigeons in it. So because of that, the pigeonhole principle doesn't apply to something like this when we have specifically said which hole. So, the pigeonhole doesn't tell us anything about how many pigeons, which in my problem are cards, are in a specific hole, which in my problem are suits. Okay, so as a result, I can't use pigeonhole principle on this, and we have to instead use logic. So I'm going to think about what would the worst case scenario be here as I'm selecting cards before I pick 3 hearts. Well, the worst case scenario is I start off by picking everything else first. That's not a heart. Which should be first, I pick 13 diamonds. Pick 13 diamonds, we pick 13 clubs, and we pick 13 spades. So let's pick all the things that are not hearts first. And once we do that, we're only left with hearts. So now I would have to pick 3 of the remaining cards, which are all hearts, before I have 3 hearts. So then I pick 3 hearts. That's the longest I could delay picking 3 hearts. So, what's the total? What is my answer here? I add these up, and I get 13 plus 13 plus 13 plus 3, which is 42. 42 cards. We have to pick 42 cards at least to be able to guarantee that we have at least 3 hearts. So just to summarize this key idea, the pigeonhole principle tells me, it tells me that there's got to be some hole with at least this ceiling number of pigeons. But if I'm doing a problem that specifies which hole we're talking about, then we can't use the pigeonhole principle. Then instead, we kind of have to use we have to use logic like we did here to work out what the answer would be.